So what we're doing today is not actually from the textbook, right? This is just some preliminaries. We'll start with 1.1 in the textbook next class. So today we're going to review and extend our knowledge of sets and set notation, and we're going to start learning about how to write proofs. So the demo is always going to come first. That's sort of the lecture part of class, and then it'll be followed by some activities. Oops. All right, a set is a well-defined collection of things, elements, or numbers. A set is well-defined if there's no ambiguity as to whether or not an object belongs to it. So a set is defined so that we can always tell what is in it and what is not in it. A set can be finite or infinite. It can contain a finite number of elements or an infinite number of elements. So some common sets of numbers include Z, which represents these, and this is notation that is pretty universal across all textbooks. Z, like that capital Z with the extra line, represents the set of all integers. That capital Q with the extra line represents the set of all rational numbers. And R is the set of all real numbers. C, the set of all complex numbers. There are several ways to describe the elements of a set. We've got three common ways here. You could use words, just describe the elements of a set in words. You can use a roster method where you just list everything that's in the set within curly braces. Yeah, if it's infinite, that could take forever. The order that you list elements in a set does not matter. And then we have set builder notation. And this we're going to be using a lot throughout the semester, the set builder. So we're going to practice with that a little bit today. It generally looks like this. It's curly brackets, and then you have an X and then a vertical line, and you read that vertical line as such that. Okay. So this set says the set of all X's such that X fulfills some condition. Okay. So this symbol that looks like kind of a funny looking capital E means is an element of. So for example, I could say 8 is an element of Z because Z is the integers. All right, so let's do some practice. I'm going to describe the set of rational numbers using all three methods. Even though we can abbreviate it as Q, we're just going to use this for practice. All right, so somebody in words, what are the rational numbers? Can be expressed as a fraction of whole numbers. Yeah. Any number that can be expressed as a fraction of two whole numbers. Actually, I should use the word integers because rational numbers can be negative. Two integers. All right, the roster method. This one's a little tough. If I want to write out all of the rational numbers, I want to list them. It's kind of hard. Yeah. Any ideas? I can use some ... dots. I mean, I obviously can't write all of them down. There's an infinite number of them. Going to be systematic about it somehow. Oh yeah, that's not a bad idea. Do all whole numbers right off the bat. Yeah. 1 over 1, 2 over 1, 3 over 1. So that would be all fractions that have 1 as a denominator. N over 1, sure. That's really more of a set builder. We'll do that in a minute. Yeah. I just want to list them. So the standard way that we do this is we start by writing all fractions that have 1 as a numerator, right, as opposed to the denominator, which is your idea, which would totally work too. But I'm just going to show you the way that's typically done. 1 is a numerator, so we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc., right? And then I start listing fractions that have 2 as a numerator. 2 over 1, 2 over 2, 2 over 3, dot, dot, dot. 3 is a numerator. 3 over 1, 3 over 2, 3 over 3. And then we just keep doing that. Right. There's going to be some repeats here because 2 over 4 is going to be the same as 1 over 2. So I will get some repeats, but I'm not going to miss anything if I do this. Yep. Right, right. You're right. Yeah, we have some repeats, and so you do not. But because I can't actually write everything out, I'm just trying to be systematic so I don't miss anything. Yeah. But, you know, that is not an efficient way to describe the rational numbers, you know, listing them out like that. Every fraction possible. Yeah, so set builder notation. Oh, yeah, it does. Yeah, so I could just put plus or minus in front of all these. You get the idea. All right, so set builder, we can do this much more efficiently. So it's just all fractions, right? So I could just say the set of all numbers that look like this, a over b, set of all a over b, such that what has to be true about a and b? Integers. A and b have to be elements of z. Yeah, that's a funny looking E. So the empty set, set with nothing in it, is also called the null set. You can denote it as brackets with nothing in it, or a circle with a line through it, but not a circle with a line through it in brackets. Okay. This one or this one. All right, so one way to describe two-dimensional space is the coordinate plane, right? We were all very familiar with the xy plane. It's often denoted as R2 because it's two real number lines, the x and the y. Okay. Every point is given a set of coordinates, x comma y, but in this course, we're often going to use a vector to express the coordinates vertically, x, y, instead of horizontally, like we do in most classes. All right, so if I wanted to describe the set R2 using set builder notation and vertical vector notation, it would be the set of all vectors, right? X, y, such that what has to be true about x and y to create all of the coordinate plane? Yes. X and y have to be elements of R. So we call that set R2. It's the fancy R, it's the double-lined R. Yeah. All right, so we're going to take a look at the writing proofs handout together. It is not the very next page or the page after that, page after that. Page, and here's part of what's annoying. All the numbers, page numbers got cut off, but it's page 4. All right, so a proof is an argument designed to convince someone that a statement is true. Writing a proof is akin to writing a piece of music. The process is both creative and logical. There are a number of rules and customs that you have to follow, but there's no routine or procedure that you can use to write a proof or a piece of music. Writing proofs is a skill, a knack you'll develop over time with patience and practice. There are a multitude of types of proofs, but the vast majority of statements or theorems that can be proven are one of 3 types. You can use a direct proof, a proof by contradiction, or a proof by induction. Today, we're just going to focus on direct proofs. So most theorems can be written in the form, if something, then something else, right? If triangle, then square. Here, triangle and square are themselves statements, right? Things that could be true or false. So statement triangle is called the hypothesis of the theorem, and statement square is called the conclusion of the theorem. In a direct proof, you assume that triangle, the hypothesis, is true. That's just a given. It's definitely true. And then give some argument that convinces all readers that square, the conclusion, is also true. So it sounds like this. Your proof would be, we assume triangle is true, therefore such and such is true, which means that blank is true, so square must be true, and the proof is complete. So in a direct proof, assume triangle is true, argue, conclude square is true. So our goal today is going to be to prove that the sum of two even integers is even. Right, so let's just test a few in our head, like 4 and 6, those are both even, they add up to 10, even, right?
I've been wondering about this for years.
Really? That's great. So like 6 and 14, they're both even, you add them up together, you get 20, also even. So it seems like it's true, like as many times as we check it, we're like, oh yeah, that seems like it's true. We want to actually prove it today. Okay, so first, we write the statement in if-then form. If n and m are even integers, then n plus m is even. Right? So we just wrote it as an if-then statement. Okay. Next, we assume that the hypothesis is true, namely that n and m are both even. That's just given. We start with that assumption. N and m are even integers. We then construct an argument which shows the conclusion n plus m is even, must be true. So constructing this argument is where the creativity comes in. There's no set path to follow, but for basic proofs, it's often possible to just sort of follow your nose. Okay? It's customary to then rewrite the proof, leaving in relevant details and leaving out anything that sort of led down a path that didn't go anywhere. So yeah, that's not necessarily the best of customs. It would be helpful to see the struggle necessary to create a beautiful proof. But nonetheless, we follow the custom of polishing up your argument and leaving out irrelevant things when you're done. Okay, yeah, like when you create a piece of music, you don't include all the various versions and missteps as you were writing it. You just record a final perfect version. All right, so Theorem 1. The sum of two integers is an integer, and the product of two integers is an integer. So we're going to assume this today. When you add two integers together, you get another integer, and when you multiply two integers, you get another integer. Everybody believe that? Okay. First definition, an integer n is even if it can be written as 2 times something, right? So 12 is even because it can be written as 2 times 6. And 16 is even because it can be written as 2 times 8. So that's going to be our definition of even. It's even because it can be written as 2 times another integer. Now, Theorem 2, the sum of two even integers is even. We're going to prove it together now. So step 1 is assume the hypothesis. So we're going to assume n and m are even. Assume n and m are even integers. Okay. Now, using the definition of even, that means that n and m can both be written as 2 times something, right? Okay. So thus, n can be written as, say, 2 times k, and m, I'll use 2 times j, because they're not necessarily 2 times the same number, right? So m will be 2 times j. So we have 2 different even numbers here, where k and j are both integers. So n is 2 times an integer and m is 2 times an integer. Therefore, n plus m is 2k plus 2j, just a little substitution. And what do you notice about 2k plus 2j? What? Yes, you can factor out a 2, right? So factor out a 2, so that's 2 times k plus j. And k plus j, by theorem 1, k plus j is an integer, right? So we've written n plus m as 2 times an integer. That means it's even. Okay. So now we just have to write up our concluding sentence. Since k plus j is an integer, n plus m must be even. Yeah. Yeah, I mean, yeah, that's the convention. If you're writing it for yourself, you don't have to. Yeah. Correct. Well, you're going to be proving that later in your activities. All right, so that's it for the lecture portion. For your activities, just quick note that the group activities are never collected unless I also assign them as homework. But working and struggling through them with your table mates is essential to building your understanding. And an answer key usually follows the group activities, but check your answers with your neighbors before you look for the answers in the packet. And if your group gets stuck, I don't have any flags, raise a hand. And you're going to be working with your classmates all semester. Many of you know each other, but some of you don't. So write down the names of your table mates and memorize them for next class. They'll be very impressed.